Integration of decomposed rational functions. Okay, so we've spent time learning how to break down complicated rational functions into simpler parts using partial fraction decomposition, or PFD as we often call it. Now, this slide marks the very last stage of that process. Let's recap briefly. We start with a messy fraction, and PFD allows us to rewrite it as a sum of much simpler fractions. Think of it like taking a complex machine apart into its individual, manageable components. This slide tells us that after you've successfully done that decomposition, the final task is to integrate each of those simpler fractions. That is, to find the antiderivative of each of those simpler fractions. And here's the good news. These simpler fractions aren't random. They all fall into a few common patterns. Because of these patterns, we don't have to reinvent the wheel every time. We can use a set of standard integration formulas we'll be going over in the next few slides, to quickly and accurately find the integral of each component. Essentially, we're going to learn a toolkit of formulas that match these common patterns, allowing us to efficiently integrate the decomposed function and arrive at our final answer. So, PFD gets us to the integration, and these standard formulas help us do the integration. We'll be building on everything we've learned so far, so make sure you're comfortable with the idea of breaking down those complex fractions before we move on. 1. The core principle. So the first point here is about the linearity property of integration. What this means, quite simply, is that if you have an integral of a sum of functions, you can integrate each function in the sum separately and then add the results. It's a really powerful property that makes our lives much easier. Now, let's look at the equation. We've decomposed our original integral, which was the integral of p of x over q of x. That's just representing our complex rational function into a sum of simpler integrals. The equation shows this decomposition. The integral of p of x over q of x dx is equal to the integral of a over x minus a dx plus the integral of b over x minus a squared dx plus the integral of cx plus d over x squared plus bx plus c dx. Let's break that down. P of x and q of x are just general terms for the numerator and denominator of our original rational function. After partial fraction decomposition, we've expressed the original fraction as a sum. Each of these individual integrals, a over x minus a b over x minus a squared, and cx plus d over x squared plus bx plus c, represents one of those simpler fractions we created. A, b, c, and d are just constants that we found during the decomposition process. A, b, and c are also constants. The key takeaway here is that once we've done the decomposition, integrating the original complex function becomes as simple as integrating each of these individual terms. And that's exactly what the last bullet point says. We simply apply the appropriate integration rule to each individual term. We'll be covering those rules in detail on the next slide, but the idea is that each of these integrals will fall into a standard form that we can easily solve. So we'll tackle each integral one at a time, using the correct formula for each, and then add all the results together. Okay, let's move on to slide 2. Now, remember from the previous slide, we talked about how partial fraction decomposition breaks down a complicated rational function into simpler fractions. This slide explains how we actually solve for the integral once we've done that decomposition. This slide is really about setting up the final step. We've broken down the problem, and now we're ready to solve it piece by piece. Keep this in mind as we move to the next slide, where we'll learn the specific integration formulas for each of these types of terms. 2. Essential integration formulas. As you recall from the previous slides, after PFD, we end up with a sum of terms, and we can integrate each term individually. These terms will fall into a few common patterns, and that's what we're covering here. We'll look at 4 primary types of integrals, categorized by what's happening in the denominator of each fraction. Let's start with A, the logarithmic form. This one comes up when you have a constant in the numerator and a simple linear expression in the denominator, something like x minus a. The integral of 1 over x minus a is simply the natural logarithm of the absolute value of x minus a plus our constant of integration, c. So, we write that as integral of 1 over x minus a dx equals log of the absolute value of x minus a plus c. Now, it's crucial to remember the absolute value. The natural logarithm is only defined for positive numbers, so the absolute value ensures we don't run into any domain issues. Next, we have b, the power rule form. This appears when you have a linear factor in the denominator, but it's raised to a power greater than 1. For example, something like x minus a squared or x minus a to the power of n, where n is greater than 1. We treat this as a negative exponent. The integral of 1 over x minus a to the power of n dx is the same as the integral of x minus a to the power of negative n dx. Applying the power rule for integration, we get x minus a to the power of negative n plus 1 divided by negative n plus 1 plus c. Let's look at a specific example. If n equals 2, meaning we have 1 over x minus a squared, the integral becomes negative 1 over x minus a plus c. Moving on to c, the inverse trigonometric form. This one shows up when you have an irreducible quadratic expression in the denominator, meaning a quadratic that can't be factored into linear terms, and a constant in the numerator. The integral of 1 over x squared plus a squared, dx, results in 1 over times the arctangent of x over a plus c. Remember, arctangent is also sometimes written as tan inverse. Finally, we have d, the logarithmic quadratic form. This is a bit different. Here, the numerator is the derivative of the denominator or a constant multiple of the derivative. For example, the integral of 2x over x squared plus a squared, dx, is the natural logarithm of the absolute value of x squared plus a squared. Plus c. More generally, the integral of f prime of x over f of x dx is the natural logarithm of the absolute value of f of x, plus c. This is a really useful pattern to recognize. Okay, so we've talked about how to break down complex rational functions using partial fraction decomposition. Now, we need to actually integrate those simpler fractions we get after the decomposition. This slide is all about the core integration formulas you'll use most often. Keep these 4 formulas handy, because they'll be your go-to tools for integrating the decomposed rational functions. In the next slide, we'll put all of this into practice with a step-by-step example, and then we'll look at some common mistakes to avoid. 3 step-by-step application example. We're starting with the integral of 5x minus 3, all divided by the product of x minus 1 and x squared plus 1. And through partial fraction decomposition, we've simplified this into 2 separate integrals. The integral of 1 divided by x minus 1 plus the integral of 4x minus 1, all divided by x squared plus 1. So, this is where we begin. Step 1. Integrate the linear term. Now, this first integral, the integral of 1 over x minus 1, perfectly matches one of our core formulas we discussed earlier. Recall that the integral of 1 over x minus a is equal to the natural logarithm of the absolute value of x minus a plus our constant of integration, c in our case, a is 1. So, applying that formula, we get the integral of 1 over x minus 1 is simply the natural logarithm of the absolute value of x minus 1. Step 2. Split the quadratic term. Now, let's look at the second integral, the integral of 4x minus 1 over x squared plus 1. This one isn't directly in a form we can use right away. So, we're going to split it up. We can rewrite this as the integral of 4x over x squared plus 1 minus the integral of 1 over x squared plus 1. This allows us to apply 2 of our standard formulas separately. Step 3. Integrate the logarithmic quadratic part. Let's focus on the first part of that split integral, the integral of 4x over x squared plus 1. Notice we can pull a constant out front. Specifically, we can rewrite 4x as 2 times 2x, so we have 2 times the integral of 2x over x squared plus 1. Now, this exactly matches our formula for the logarithmic quadratic form. Remember, the integral of 2x over x squared plus a squared is equal to the natural logarithm of the absolute value of x squared plus a squared. In our case, a squared is 1, so a is also 1. Therefore, 2 times the integral of 2x over x squared plus 1 gives us 2 times the natural logarithm of the absolute value of x squared plus 1. Step 4. Integrate the inverse tangent part. Now, let's tackle the second part of our split integral, the integral of 1 over x squared plus 1. This is a perfect match for our inverse trigonometric form. The integral of 1 over x squared plus a squared is equal to 1 over times the arctangent of x over a here. A is 1, so 1 over a is also 1. Therefore, the integral of 1 over x squared plus 1 simplifies to simply the arctangent of x. Step 5. Combine all results. Finally, we bring everything together. We started with the integral of 5x minus 3 over x minus 1 times x squared plus 1. We decomposed it, and now we've integrated each part. So the final answer is the sum of our individual integrals. The natural logarithm of the absolute value of x minus 1 plus 2 times the natural logarithm of the absolute value of x squared plus 1 minus the arctangent of x, and of course, don't forget to add our constant of integration, c, and that's it. We've successfully integrated a decomposed rational function. Okay, so let's tackle an example to really solidify how we integrate these decomposed rational functions. Remember from the previous slides, we've already done the hard work of partial fraction decomposition. This slide shows us what happens after that crucial step. Remember, this process relies heavily on recognizing the patterns and applying the correct formulas. We'll look at some common mistakes in the next slide to help you avoid those pitfalls. 4. Real-world analogy. Imagine you are tasked with cleaning a very large, cluttered room. Think of this room as representing our original, complex rational function. It looks daunting, right? Instead of trying to clean the entire room all at once, which would be incredibly difficult, you decide to divide it into smaller, more manageable sections. Let's say you break it down into the bookshelf, the desk, and the floor. This division is analogous to what we do with partial fraction decomposition. Remember from the previous slides, PFD breaks down that complex fraction into simpler fractions. Each of those simpler fractions represents one of these sections of our room. Now, you wouldn't use the same cleaning tool for every section, would you? You'd use a duster for the bookshelf to gently remove dust, a wipe for the desk to clean surfaces, and a vacuum for the floor to suck up dirt. Each tool is best suited for its specific task. Similarly, we use specific integration formulas, the ones we just covered, for each of those simpler fractions we get after performing partial fraction decomposition. Those formulas are our cleaning tools. Finally, once you've cleaned each section individually, the bookshelf is dusted, the desk is wiped, and the floor is vacuumed, the entire room is clean. And that's exactly what happens with integration. Once we integrate each of those simpler fractions, we combine the results to get the integral of the original, complex rational function. Okay, let's move on to a real-world analogy to help solidify our understanding of integrating decomposed rational functions. This slide aims to give you a more intuitive grasp of the process we've been discussing. So, this analogy should help you remember that breaking down a complex problem into smaller, manageable parts, and then applying the appropriate technique to each part is a powerful problem-solving strategy, both in cleaning and in calculus. We'll now move on to look at some common mistakes to avoid, so you can ensure you're applying these techniques correctly. 5 common mistakes to avoid. Okay, let's move on to slide 6. This slide is really important because it highlights some of the most frequent mistakes students make when integrating decomposed rational functions. We've spent time learning how to integrate these, so now we need to make sure we avoid these common pitfalls. First, let's talk about forgetting absolute values. You'll often see students write the natural logarithm of x minus a, and that's not quite right. Remember, the natural logarithm, or log, as we often write it, is only defined for positive numbers. So, we always need to include the absolute value. The correct way to write it is the natural logarithm of the absolute value of x minus. This ensures that the argument of the logarithm is always positive, regardless of the value of x. It's a small detail, but it can make a big difference in your answer being correct. Next, we have the incorrect power rule. A very common mistake is trying to apply the simple logarithmic rule to integrals like 1 over x minus a squared. So, students might incorrectly integrate 1 over x minus a squared as the natural logarithm of x minus a squared. But remember that basic logarithmic rule, integral of 1 over x minus a dx equals the natural logarithm of the absolute value of x minus a plus c, only works when the denominator is simply x minus a to the power of 1. If you have a power greater than 1, like squared, cubed, or any other power, you must use the power rule for integration, which involves reducing the power and dividing. Now let's look at ignoring the constant a in the inverse tangent function. When we integrate something like 1 over x squared plus a squared, we get 1 over a times the inverse tangent of x over a plus the constant of integration. Students often forget to include that 1 over a outside the inverse tangent function. It's easy to overlook, but it's crucial for a correct answer. Finally, we have sign errors during splitting. When you've decomposed your rational function and end up with a term like bx plus c over x squared plus a squared, and you split it into two separate integrals, be extremely careful with the sign of c when you move it into its own integral. It's easy to make a small sign error that can throw off your entire calculation. So, keep these common mistakes in mind as you practice. We'll wrap things up with a quick review of the key takeaways on the next slide, but mastering these points will really help solidify your understanding. 6 key takeaways. Okay, let's recap everything we've learned about integrating decomposed rational functions. This slide, our final key takeaways, is essentially a cheat sheet to help you quickly identify the correct integration technique. First, let's look at linear factors leading to logarithms. If, after your partial fraction decomposition, you have an integral of 1 over a linear expression, and I mean something like 1 over the quantity x minus a, then the integral of that is the natural logarithm of the absolute value of x minus a. Remember that absolute value is crucial, as the logarithm is only defined for positive arguments. Next, we have repeated linear factors and the power rule. If you encounter an integral of 1 over a linear expression raised to a power, say, 1 over the quantity x minus a all raised to the power of n where n is greater than 1, then you need to use the power rule for integration. The integral becomes the quantity x minus a raised to the power of negative n plus 1, all divided by negative n plus 1, plus our constant of integration. Moving on, let's consider quadratic factors with a constant numerator and the inverse tangent. If your decomposed integral has a constant, just a number, over a quadratic expression, like 1 over x squared plus a squared, then the integral is 1 over times the arctangent of x over a plus our constant. Remember, arctangent is also sometimes written as tan inverse. Now, let's look at quadratic factors with a variable numerator and logarithms. If you have a variable expression in the numerator, specifically something like 2x over x squared plus a squared, then the integral is the natural logarithm of the absolute value of x squared plus a squared, plus our constant of integration. Notice this is similar to the linear case, but applied to the quadratic expression. Finally, and this is extremely important, don't forget the constant of integration, plus c, at the very end of every indefinite integral. It represents the family of all possible antiderivatives. It's a small thing, but it's a common mistake that can cost you points. So, to quickly summarize, think of it this way. Linear factors give you logs, repeated linear factors need the power rule, constant over quadratics give you arctangents, and variable numerators over quadratics give you logs again. Keep these rules in mind, and you'll be well equipped to tackle any integration problem involving decomposed rational functions. Now, are there any questions about these key takeaways before we move on?